Okay, it says record.
Hello, YouTube.
All right, let's start. So, this is the last lecture. I said I'll do some sort of overview of complexity because that is what most people seem to want. And then once the camera stops rolling, I'll tell you more about the final in this, right? Okay, so sort of an overview, brief, high-level overview of computational Do you get it? Unfocused. Yeah, is that better? Maybe it's yeah. Okay. So, brief overview of computational complexity theory. So this is going to be somewhat stream of consciousness-ish. So you can sort of pause and ask me questions of you want me to say more about one thing or another thing. We'll do about 45 minutes of this and then I'll take questions. And so what you've seen so far is P versus NP, which is sort of like the first steps of thinking about computational complexity theory. But what is this theory about? It's about trying to classify problems or languages by the amount of computational resources required to solve them, and by I'll sort of say the most efficient or economical, meaning that you'd like to classify problems by sort of the, I say, most efficient, economical, or the minimum amount, or you can think of the minimum amount of resources required to solve them. So this is like trying to come up with the most efficient algorithm, or the most optimal algorithm. But I said resources, because so far what we've actually talked about in P is time. That's a resource. And NP is sort of like non-determinism, is another resource, like the ability to interact with a verifier. But what would be a third resource that you would think about? Space, exactly. So there's space, and you can also think about randomization, like the ability to flip random coins, and you can also think about, we'll get to that, something about interaction. So let me sort of write these things down. So resources. So the obvious one is just time, right? Just the running time of the algorithm. Space, which is sort of the memory requirement. Memory requirement of the algorithm. So again, a lot of what I'm saying is sort of very high level, right? I'll switch between talking about Turing machines and algorithms, and so if anything is unclear, just stop me. But I don't want to get into I'll try to sort of minimize the amount of mathematical symbols I'm using, given that it's the last lecture. Right? If you guys agree. So time, space, another resource is non-determinism. And so you can either think of this as the amount of time in a non-deterministic machine, but more generally, you can think of it as like, given any machine, you can make it a non-deterministic one. And this you can kind of think about as sort of in terms of the ability to use verifiers. It's kind of what non-determinism is, and I'll talk more about this as we go along. So let's just start with these three resources. I'll try to show you sort of what's going on, and then we can try to talk about other resources if we have time. Now, a few concepts that will be useful to talk about are what are called co-classes. So what this means is, given any class C of languages. So usually for languages, I'll use script letters, and for any class like P or NP, I use bold, or technically \macdb in logic. That's what I'm using. Okay? So given any class of languages, the co-C class is essentially L complement, where L is in my class. Right? So I take any class and I take the complement language. Any language, I take the complement. Like this is the co-class of this class. So one thing, whenever we come up with a class, is to ask, is the co-class the same thing? Like if this is the class of decidable languages, then co of decidable languages is the same thing as decidable languages. But if this is RE, then that is co-RE, which are different. Okay? And then we'll talk about C complete. So the way to think about C complete is like it's the hardest language in C. The hardest language in C. Now, I shouldn't have used C. This is used for complex numbers. But, yeah?
C here means P or NP.
P or NP, or we'll talk about all kinds of other strange creatures, strange language like classes. And so for P or NP, of course, for P complete it becomes a little weird. But the hardest language in C, and this usually means that, so I'll say L is C complete if for all L prime in C, L prime efficiently reduces to L. Right? And that's the reason this is the hardest language is if you can solve L, then you can solve everything in this class. Does that make sense? So this is the hardest, and we'll often, for every class, try to come up with some sort of canonically hard problem. Okay? That sort of describes what's happening in that class. So far, so good? Okay? So let me just write down the classes that you've seen so far. So firstly, you have P, which is polynomial time languages, or technically languages decidable in polynomial. Right? This is where everything starts. And in some sense, the whole origin of this theory is to try to understand what can be done efficiently. And because that, in some sense, that's like, from the view of this theory, an optimal, like the best we can hope for, and you'll see actually there are even better things. But when you start out, the best you can hope for is a polynomial time algorithm. And of course, you might say, no, I actually want a linear time algorithm. But then that's a much more refined view, and we will, like, that's more recent developments in this theory. But let's start with polynomial time. So then let's talk about NP, which is non-deterministic polynomial time, which is the same thing as the sort of notion of verifiers, right? So let's have a language